Hello, math fans. We're going to talk about a little bit more math here. I'm going to talk about something called graph theory. I'm going to provide some structure to a few questions that popped in my head many years ago when I was thinking about this idea of how could you select if you're choosing a tournament. It might not be just March Madness, but you're given several draws. How can you be sure that one of them is pretty good? And that got me thinking about this idea of like, how can we guarantee something? All right. So, but mostly I want to use this as an opportunity to show you how, and sometimes in math, one way we add structure to something and allow us to ask questions. Often that's the hardest part, is giving, something to work around. And I don't know that I've done a good job here, but I'm giving a start and asking a few questions. And I have a few very small results. And I don't really have time to devote to this. And so again, I'm passing this on to someone else in hopes that they'll mention me when they actually solve these questions. So my thought was this: if you give me two draws and you say you must, with 100% certainty, get at least half right in the first round, you can do it. How can you do it? Think about it. So this is more not thinking about choosing in a good way, just choosing a way that you know for certain. And so you could do this. You could pick all the seeds and then flip your draw and make the second draw all the opposite ones. Pick all the higher seeds in one draw and all the lower seeds in the other draw. In the first round, one of those is going to be at least half right. So that's what I mean by how could you guarantee? One of them will be terrible in the long run. And that's not really a good strategy because there's too many games beyond the first round. But that got me thinking about what could you guarantee if you're allowed to have a collection of draws. And I realized it was a hard problem. And so then I started to think, well, how would I measure the distance between two draws? And the collection of all, there's a lot of draws, but are some of them kind of close together? Because the stats suggest that I think the best ever was somebody getting, this was a couple years ago, so I might be out of date, but was getting 55 of the 60. At the time it was 63 games, correct. Now it's 67 games. So it looks like the best ever is, getting, if you can get within 8 games of the winner, you're winning your pool or whatever. So that got me the question of, okay, how can I get within, how could I guarantee that I'm within 8 games of a perfect draw? Okay, so there's sort of a question to ask. So, that can be the open question. Again, someone maybe has studied this. I'm no expert. I'm just asking questions. But, how many draws do we need to fill out in some unusual way? Do we need so that at least one is within, I don't know, for now, let's say 8 of the perfect draw? And that's not the question I'm going to ask here. I'm just phrasing that as a big question. What would be the number? Do you need 1 billion draws? Do you need 70 draws? Right? So what is the scope of this? Can we answer that question? And what about if you change this number to, I'm okay if I get within 10? Then you're going to need quite a few. So this gives the question of how could we tweak that to get to a reasonable number? Okay. And I thought about that, and I wrote a bunch of things, and even had a spreadsheet I filled out where I was trying to measure, I'll talk about this other stuff in a second, trying to measure the distance between draws and trying to define it in some way. This is the work I found from many years ago in this spreadsheet. But at the time, I felt like I didn't get a good definition, but I feel like I have a better one now that actually might have some legs. But I think it's interesting enough because there's so many tournaments out there. I mean, I played tennis. You've got Grand Slam tennis tournaments. Single elimination tournaments are pretty common. And so it might be interesting to give this some structure. Okay, so then I've pulled back and I said, well, let's make this smaller. Let's say I have 4 teams, and then let's say I have 8 teams. And let's think about all possible draws that can happen. And I've got some notes I'm going to just open here because I have it on the wrong page. I did earlier today. So then I just started to think about the collection of all draws. That's what we do in math. We say, let's think of that as an object. Let's think of that as our arithmetic. That's what we do a lot in like abstract algebra and higher level math courses. So we give it some structure. And sometimes that leads to really remarkable results. Sometimes it doesn't. Okay, so let's think about what can happen and somehow encode this. And I don't know if this is a good encoding, but I'm just going to do some examples and then we'll finish with kind of where I'm going to leave it. And this won't take too long, I don't think. So you could have, the 1 seed win here. You could have the 2 seed win here. And then you're going to have the final, and let's say the 1 seed wins. So earlier today, I was just trying to encode this. So I started to go, I'm just going to write 1, 2. 1 means the 1 won the semifinal, the 2 wins. And then I put, I don't know if this was a good notation, but I put a semicolon 1. And that was one of the draws. Now, if you've watched my previous videos, you know how many draws are over here. There's 2 to the 3rd draws because there's 3 games, 2 choices for each. So there's 8. So then I did the following. I started to write them out. I started to go, well, you could have 1, 3, 1, meaning the 3 wins and 1 wins. And then I put a little line between them saying the only difference between those is 1 game. And the 1 game would be this game. Okay, so I started to think, let's just define a distance of 1 between draws. Because if I know what draws are a distance of 1, then I can figure out which are a distance of 2 and which are a distance of 8. And that was the key new thought I had. Again, when I thought of this in the past, I didn't really do that much with this. Okay, so let's keep going. And I feel bad I didn't think of this the first time, so I'm going to do a 13. But the 3 wins. So 1 and 3, but the 3 wins. That's 1 different than this one, 2 different from the original one. And I kind of didn't know the structure, to be honest, when I first started doing this. So then I did some more. I just kept experimenting. So I said, well, what about this one? How can I go from there? And so I was like, well, if we have that scenario, I know this is more abstract than the other ones, but I think this is leading somewhere. So stay tuned here. So this is 3. This is 3. Is there anything else I can change and only be within 1 of this? You start to go, well, this would have to be a 4. Okay, so let's fill that in. You could have 4 wins and then 3 wins and then 3 wins the final. That's within 1 of that. And you keep going in, an interesting little structure formed. Okay, so I'm building some structure on this thing. And this actually gives you a lot of information. This may help me a lot to think about this. Okay, what about this? Is there anything else I can change? And I started to realize there's really only, in each one of these cases, there's only 2 connections for this small one. And this is what I tell students to do small cases. And there probably is a nice theory to this. I am not an expert on graph theory. I have an interest in it, but okay, what else could we change? Well, we could have had team 4 win that. 4, 3. All right, so we're building this structure. Mathematicians have a lot of patience for this because we can see a benefit. And I'm going to work my way back. And it formed this little cycle. So it was just a cycle of everything was connected twice, and it was a good little journey. So I'll write out what the other things were rather than have you keep thinking about it. But I had 1, 2, and 2 wins. 1 wins the first semi, 2 wins the second. And then I had 4 wins the first, 2 wins the second, and 2 wins the title. And then I had 4 wins the first, 2 wins the second, and 4 wins the title. And that's all the cases. We call that a graph. Think of each of these as a dot. And so we'd have this dot, 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 dot. We call this an 8-element graph. We call those vertices. And there's a lot of things that can be studied with graphs. Graph theory is a relatively new field. Meaning 100 years or a little more. No, that's wrong. Euler used graph theory in a way. some of the modern methods. It's more modern in terms of, so I'm wrong. It's several hundred years old. Anyways, so here you go. There's this graph. So we say that each one has, it's a few terminologies, has degree 2. It has 2 connections. So there's a term for this. We would call this 2 regular. And again, I'm no expert on these terms. It's 2 regular. It has 8 vertices. Okay. So you could ask this question here, which is if you're allowed to only pick one draw, how far away from the correct answer might you be? So let's say you just make this draw, the seeds. Well, you're going to be within 1, 2, 3, 4. That's called the diameter of the graph. You're 4 away, within 4 of everything. Okay, so then you could say, well, what if I wanted to be within 1 of everything? Well, then I'd have to pick these draws. You can see this kind of opens the door to something else. So unfortunately, you would need 3 to be within 1 of everything. But what if you wanted to be within 2 of everything? Can we do that nicely? Looks like you're still going to need 3. But what about if you want to be within 3 of everything? Well, that takes care of it. So 2 draws will be within 3 of everything. I don't know if that's good or bad, but that's the sort of question I want to ask. Okay, so then I was like, let's bump it up. And I started to write this out today. What can happen? And I was like, oh, this is complicated, but I was willing to persevere a little ways, and this is about as far as I can go before I need to go work on my actual work. And I was like, okay, so what are we going to call that? Let's call that 1, 4, that's how I wrote it down, 2, 3. And then I said in the next round I had 1 and 2 win. In the next round I had 1. And then I realized that once you get down to here, you're back to that smaller case. And so you get another one of these little things, this little collection of 8 that's connected. Then I was like, okay, now I got to actually deal with what happens if I change. And I did one, I just changed one of the numbers, 6, and I kept everything else the same. And then I realized I could keep all the rest the same, and then these would all be connected, and I started to get this structure. Okay? And then there were a few other little things I saw, that this was connected to this by 1, and there were a few connections between them, and I went, oh my gosh, this is complicated. But I persevered a little further, and I actually, this looks crazy. It's taking too long, so I decided to just make the video and leave this for later, because I can't spend any more time on this today, or probably for a few weeks or a month. This is the problem. I don't have time to work on these projects, but I hope eventually someday I can have some people work with me on them or work with them. So I put down all of them. I found the pattern. There's 128 of them. There's a lot. Holy cow. And then I started to look for connections because it was getting so big. And I was like, oh, everything is connected 4 times. I probably should have been able to see that right away, because you can only change certain things if you're only going to allow 1 game difference. And that really started to give me some ideas. Now, I've only gone this far. I was going to actually draw the graph, but I realized it was so big that I'm going to need some tools. I might have to ask somebody. Okay. So that was enough. I got far enough that I was able to say a few things. All right, so there's 128 type draws. The vertices are draws. And how each one it's 4 regular, meaning each one is connected to 4 other draws. And I started to think maybe that's enough to start asking some questions. Okay, so then bring in the big dog here and see what we can say. But I hope this kind of shows you this idea. And I'll show you this now before we get into that. So a 4 regular graph is something where there's 4 connections. And there's all sorts of examples. Here's an example. I've never heard of this graph before. It must be important. It has a name. But you could start asking questions like, if our graph looks like this one, could we pick, a few dots that would be within, 3 or 4 of everything? That's the question I want to ask. Here's one with 20 vertices with this crazy drawing. Oh, I should go back to this other one because this other one has a better drawing. Here you can see that if you picked definitely if you picked a couple of these outer ones, this outer one is connected to like a whole bunch of the other ones. So you'd only need like one or two to be within two of everything. All right. This graph, the Folkman graph here, whatever that means, is one with 20, and everything, there's 4 coming out of them. Again, I don't know what ours looks like yet because I've not gotten through making it. But you could start to go, could I pick a few of them that would be within a couple of each thing? This is like degrees of separation. What about this graph? This has 70, so this is closer to what ours could look like. And then you could ask, is there a way I can pick in there? And I'm sure that's equivalent to some sort of graph theory question, but I can't quite figure out. Something to do with the girth or the spread or the diameter and how you can pick. But I'm going to need help from an expert on that. But we have those. Okay, so let's finish here with, I then said, can we extend these ideas? And I started to realize, yeah, we can. So if you pretended it was seated 1 to 64, and you put a 1 in the middle here, maybe I can make this a little fatter here. All right, so we're going to put this a little bigger. So if we put like a 1 here, and then the 1 came from, I don't know where we usually have our 1 come from, over here. So we'll say this is a 1, and this is we'll number them like this. So 4, because you'd have in the NCAA tournament, they have a whole bunch of 1 seeds, but let's pretend it's 1 through 64. So over here we'd have the 3, and we'd have the 2, and then going back, we could talk about, wherever the 4 comes from, just like I had filled out before. So there's a 4 and a 5. There was a 1 and an 8. I don't know why I didn't write it the same way. There was a 2 and a 7. There was a 3 and a 6. And you could keep backtracking and saying, okay, I would like to start with the one that has the seeds and then think about what I can change to only change things by 1. Well, I can change this, and that will change 1. But if I don't change that, then I can't change any of the other ones. So that locks down all of these 1s. Okay, so then you go to the next level, and you say, okay, you can change the 1. You could change this 2, because you could have made it a 3 and left everything else the same. So you start when I didn't fill that in. So we have a 1. We have a 1 and a 2. So I could change that 2. I could change this 4. It's not going to affect anything. I could make it a 5 instead of a 4. I could change... I can't change any of these 2s anymore, because if I did, I'd be changing 2 things. I could change this 3. And you start to realize, oh, that means there's only 1 thing I can change here, 1 thing I can change here, and 2 things I can change back here. So there's only 4. That's the 4 regular part. I'm only connected to 4 things. If you go back another step, you say, well, I can't change that 4, but I could change this 5. I can't change the 1, but I could change the 8. I can't change the 2, but I could change the 7. I can't change the 3. You get 4 more. So when you go to the next one, it's 8 regular. And each time when you step up another level, the next one there will be 8 more. So it's 2 more, 4 more, 8 more. So I've convinced myself of that. And so that leads me to our structure, a starting structure for studying the distance between draws. That's probably an interesting graph theory question. So we just went through and talked about if you have 4 teams, there's 8 draws. We showed you that picture. And so I just want to kind of have someone study the structure a little more. Maybe there's a practical piece at the end of like, how could you pick 20 draws? But I think that would be the stuff you would need to answer the question. I would like to study this graph a little more and say what we can say about it, and then ultimately we'd like to say something about this graph. And I think that's only for 64. We're going to need to add a little more, but I just want to keep it with the theme. That might give us a chance to attack this question. Meaning, I would like to look at this graph where each dot has 32 things coming out of it. And I would like to know what I would need to do, how many draws I would need, and so that I'm within 8 of everything. And I have a feeling that's a relatively small number because of all the connectivity in there. Now, I'm sure people have studied questions like that, but I feel like that gets at the heart of my original question. How do I pick here from this graph that will tell me how to choose my draws? Okay, so I think there's some interesting graph theory questions. And I think this is interesting to sort of, this illustrates this idea of how do we give structure to something by defining, I was defining a distance, the distance between true draws, and I defined it to be, they have one game that's different. And it's amazing how that little bit of structure allows me to pull in a lot of other math. And so often that's what we're trying to do, is give things structure in math, make it a little more abstract. People don't understand that, but if we can do it, that's really the prize. Then we can study it. And sometimes that leads to these big results. So I thought that was an interesting little journey through how we try to add and study such a thing. So there you go. This is basically graph theory on single elimination tournaments. I think my result for here is that for a given tournament, you get some sort of regular graph where each thing has the same number of named degree coming out of them. And I think that's something we could then study. It would be interesting to look at those graphs and say what else we can say about the structure, because anything we can say about this structure will give advice about how to fill out your draws if you have 20 or 30 draws in the NCAA tournament. All right. So there you go. I'm going to stop there, but I hope you found something interesting.